Very good morning to all. In this lecture, we are going to see about some important terms and definitions in order to analyze the performance of the power plant, or it may be a substation and power grid. Load curve. The curve showing the variation of load on a power station with respect to time is known as load curve. We can plot the load curve, either it may be on the power station or it may be on the power grid, or even we can also make a load curve on a substation. This load curve we can be able to draw on a daily basis, or it may be a weekly basis, monthly basis, or even for a year. If we draw for a complete 24 hours, then this will be a daily load curve. If it is for a 24 into 30 days, then that will be for a monthly load curve. Even sometime they will take the average of 24 hours, that means a complete day we will get. So if we take the average of complete data, then if we plot in the same way on every 30 days, then we will get a monthly load curve. In the same fashion, if we calculate the average load of month, then if we plot for the complete 12 month, then we will get annual load curve. From this load curve, we can easily point out what is the variation of power consumed by that particular area, or it may be a particular generator, how much power it generates to satisfy the load demand, that we can able to observe from the load curve. Time to time we can easily observe how much variation is observing in that particular area, or it may be in the generating station. The figure it shows here from midnight 12 to the next midnight 12 o'clock, that means 24 hours data. And if you see here, x-axis it denotes a time and y-axis it denotes a power. And from this curve we can easily point out where our peak load is occurring. If you see here at this time, that is exactly between the 5 o'clock to 6 o'clock, the peak period is occurring. And also we may be able to observe what is the base load. Base load is the minimum load that all the 24 hours that it has to consume. See, if you see here, this is the minimum load point that always it observes here. And also from this same load curve, we can easily able to get the energy consumed on that particular day. The area under this curve, if you calculate, then that's the total amount of energy consumed on that particular day. For example, consider a daily load data. Here the table shows for a 24 hours the load pattern. Time is in hours, average load is in megawatt. That means the first hour, the total amount of power consumed on that particular area is 1341 megawatt. And if you across at hour 10th, the total amount of power consumed is 1225. So likewise, for all the 24 hours, the average load of that particular hour is taken, and we will consider for further analysis. Average of these all 24 hours is 1362.63 megawatt. That means for the complete day, the average power consumed by this Delhi area is 1362 megawatt of power. And again, if you see the same data, the peak load at what time it occurs. If you see here between the 19th and 20th hour of the day, the area completely it consumes a peak load. peak power is consumed on that particular time. If you see the base power of the complete day, then what is the minimum amount of power consumed is 1203, that is occurring between 5 o'clock to 6 o'clock. And further, this is the total installed capacity available for that Delhi region, that is 3677 megawatt of power. And among that one, the total amount of connected load considered is 1600 megawatt. That means we are having installed capacity of 3677 megawatt, even though only we are having a load of 1600 megawatt. There is a difference between the peak demand as well as connected load. It's not mandatory all the load of that particular areas to be in on condition, so that's why there is a deviation. On that particular area, the peak demand is only 1512 megawatt, that's all, and remaining loads are in off condition. Let's see the load curve for this particular data. Daily load curve, that means it has to draw between the power versus time. Time should be from 0 to 24 hours, and in y-axis if you see, that is in megawatt of power, that what we have seen in the example. Now if you see this all over the complete 24 hours, the curve is drawn as per the load variation. So if you want to see at particular time between 5 and 6, if you want to see, that's the exact power what happened during the time. And again, if you want to see your power at the time of 18 hour, then this is the correspective power consumed on that particular time. So the complete variation of power you can able to observe from this load curve. From this load curve also we can able to visualize what is the base load that occurs always during the 24 hours. From this point, if you say this is the least power that consumed in this on that particular day, and that means we can say all the 24 hours this power is the base power of all the time. And if you want to see what is the peak power consumed, is if you see here at this time period, that is between 19 and 20 is the area, is the time that where you are consuming a peak power. And also one more thing is, if you want to calculate the energy, total amount of energy consumed on that particular day, then if you calculate the area under this complete 24 hours, then you will get a complete energy consumed on that particular day. But with such variation of this, it's not possible to calculate the area under the curve. For this, we are going for drawing this load curve as a load duration curve that we will see in the next slide. Load duration curve. The load curve, those data, if we arranged in a descending order, then if we plot the curve, then we will get the load duration curve. In that case, we no need to talk about in x-axis about the times in hours or not, because you have sorted completely, there is no any arrangement. So instead of saying in terms of hours, we can call that as a time elements with respect to your real power, that is in megawatt. And if you see the curve, it's somewhat like a descending order, it completely arranged properly, and we can easily calculate the area under the curve. So area under the load curve is equal to the area under the load duration curve, and that means we can easily able to calculate the energy consumed on that particular area. These are all some of the importance of the load curve. Variation of load during the difference of hours of the day we can easily able to observe from the load curve. Area under the load curve is the energy generated or consumed on that particular day, or it may be a month, or depends upon the load curve. And also we can easily observe the average load as well as the maximum load, as well as we can also observe the base load, what is the base load of that particular day. Apart from this, also we can able to plan for the future, what should be the size we have to fix for the next upcoming years. If there is increase in load demand, then we have to go for increasing the size of the generating units. So this type of load curves are helpful in selecting the size of the generating units for the future expansion. Also, this load curve helps to fix the tariff of the energy. Average load or average demand. The term average load or average demand, it says on the complete day, or it may be a complete week, or it may be a complete month, what's the average load or average power consumed by that particular consumed by that particular area, or it may be, if it is a generating station, what is the average power generated by that particular generating station. Or it may be, if it is a power grid, then we can talk about what is the average power delivered to the consumer area by the particular substation, or it may be a power grid. Like that we can easily talk about that one. Energy generated, the maximum units or energy generated for a complete day or month or year. How to calculate this? So 1 unit equal to 1 kilowatt hour, and units generated per day we can calculate from average load for an hour into 24 hours. If the average load is for hour, then if you have to simply multiply into 24, that's for a complete day energy generation we will come to know. If the units generated per month, if you want to calculate, then if your average load is in terms of day, then only we have to multiply with 30. Suppose the average load is for an hour, then we have to multiply into 24 into 30. Suppose if you want to calculate annual energy consumption or annual energy generated, then we have to go for 24 into 365 days, that is total number of hours per year is 8760 hours. Simply we have to multiply this term. It's the same way, just see the example that what we have considered earlier example. So in that case, if you see the average power consumed by that Delhi area is 1362 megawatt of power. If you multiply into hour, then that's nothing but 32 gigawatt hour energy we are consumed by that particular day. Now we will see about some definitions, as I said, about the load factor, demand factor, diversity factor, and plant capacity factor. These are all some of the factors in order to understand the performance of the substation, or it may be a power grid, or it may be a generating station. Load factor, it defines the ratio between the average load to the maximum demand. So from this equation itself, we may come to know that this is the ratio between the average value of power consumed on that particular area as well as the maximum demand on that particular area. So definitely, if you see this definition, the maximum demand is always greater than average demand, and always this load factor will be less than 1. In terms of energy, if we want to say the total amount of energy generated on a particular day upon the maximum demand into on the particular day, that means 24 hours. For example, in order to analyze this load factor, to understand the load factor, just for example, we can consider a generating station. It has a capacity of 100 megawatt, and it's not necessary the generator has to always generate 100 megawatt, because the generator has to generate the power depends upon the energy requirement at the load center. And now again further consider the load center. needs the load demand of say 20 megawatt for all the time of the complete 24 hours, except 1 hour it needs the amount demand of around 80 megawatt of power. In this, if you see, for most of the time you have to operate your generating unit to generate the power of only 20 megawatt, and for only 1 hour you need your generating station to operate at 80 megawatt of power. In such case, if you see, the average load and the maximum demand are much variation. If you see that the load factor, if you calculate, then that will be very much less on comparing between the average load and maximum demand. In that case, you are supposed to operate the generating station in order to satisfy the consumer demand, and in other case you are generating the electricity at a very higher cost, and you have to collect the money from the consumers at higher rate. In other words, if you see, the consumer needs all the time 70 megawatt of power, and only for few hours if it needs of 80 megawatt of power, then your load factor that crosses that value is around 0.8 or above 80% of value. In that case, if you see, then load factor is good and you are generating the power at very low cost. So from this explanation, the load factor, we can easily observe if the load factor value is greater, that means near to 1, means you are operating the generating station at good level. Suppose the load factor is very less, then we can say you are generating the electricity at higher rate. Let's see for the example that what we have considered for the Delhi area. There we know that average amount of power consumed on that particular area is 1362 megawatt, and the peak value of power consumed on that particular day, the whole day, is for 2 hours 1512 megawatt of power is consumed among the 24 hours. So if we calculate the load factor for that complete on that particular day, it's about 90%. So that what, it's nearly somewhat equal to 1. So the Delhi plant, we no need to bother about that, the performance of that is good. Demand factor. Demand factor is the ratio between maximum demand to connected load. Maximum demand is the maximum power consumed or generated on a particular time. Connected load is different from maximum demand. If you compare between the maximum demand and connected load is always greater than the maximum demand. So again, the demand factor also should be less than 1. Now, for example, consider a house. In that house, there may be many electrical appliances that will be completely wired. And it's not mandatory that you have to switch on all the electrical appliances. But when you are thinking about a connected load, you have to calculate all the power ratings of that electrical appliances. That's called connected load here. On a particular day, if you want to operate on a daily basis and hour basis, if you want to take the reading among the 24 hours, at one point there may be a peak demand that will occur. So that peak demand, that will not be equal to the connected load value. The reason is, at peak time it's not the condition that you are switching on all the load. You can be able to switch on all the load, even though that may not be also available. So there is a difference that may happen between the maximum demand and connected load. There may be a chance, but most of the time we can't say the maximum demand is equal to connected load. Connected load is there nothing but what are all the loads are available in that particular connection, and that's not mandatory. You have to switch on all the load. So this is the difference between your maximum demand and connected load. For example, we just consider in a house the net amount of connected electrical appliances, that ratings if you calculate, then if it comes 70 kilowatt of power, and if you observe the complete load data on a particular day, then say for example the maximum power it observed on a particular time is only 35 kilowatt, then we can say demand factor is 35 kilowatt by 70 kilowatt. The demand factor equal to 50%. So like that, there is a difference between maximum demand to connected load. From this, we can easily observe how much amount of capacity we have to fix on a particular generating station, or if it is a substation, how much power we have to bring from that nearby big substation. Again, if you see, already we consider that example. From that, if you see that Delhi area maximum power is 1512 megawatt of power, and total connected load we considered 1600 megawatt, and if you see that this is 0.94, and 0.94 is again it's a good one, and we can say we are utilizing the complete plant properly. The installed whatever the power, that completely we are utilizing. Diversity factor. Diversity factor is also one of the term which it affects the cost of units generation. It is the ratio between sum of individual maximum demand to maximum demand on the power station. It may be a power station, or it may be a substation, or it may be a even power grid. For example, in order to understand this, for example, we will consider a distribution feeder, and it feeds to 5 houses. Now these 5 houses, if you check the maximum peak value of power consumption, it happens at a different time. Say for example, each houses are consuming a peak value of power at 5 kilowatt. That means if you sum up all the individual maximum power consumption, that will become 25 kilowatt. And as I said earlier, it's not mandatory all the peak power consumption, that will not mandatory to happen at the same time. Each and every house, that maximum power consumption time, that will be different. And now if you come on to the feeder session, on feeder point at which time the peak power consumption is happened, or the feeder delivers the peak power to the consumers. If you take the data on that feeder point, say for example in the feeder point, if the peak consumption is only 20 kilowatt, then the diversity factor we can calculate 25 kilowatt by 20 kilowatt, that means 1.25, which is greater than 1. If you see this diversity factor should be always greater than 1, because the reason is the sum of individual maximum demand is always greater than your maximum demand on that particular substation, or it may be a power station. And from this we can say that higher the diversity factor, is lesser will be the cost of unit generated. The capital cost of power station depends upon the capacity of the power station. Lower the maximum demand of the power station, lower is the capacity required and therefore lower is the capital cost of the plant. With a given number of consumers, the higher the diversity factor of their load, the smaller will be the capacity of the plant required and consequently the fixed charges due to the capital investment will be much reduced. Plant capacity factor. It is defined as the ratio between actual energy produced to the maximum energy that could have been produced. In terms of power, we can say it is the ratio between average demand to the plant capacity. Plant capacity factor is a very important factor in order to understand the utilization of generating unit. For example, a generating unit has the maximum capacity of 100 megawatt, then we can't say that always all the 24 hours the generating station is generating the 100 megawatt of power. That is only depends upon the load. If we say the load variation or the load demand, it needs only 50 megawatt of power on the whole day by average, then we have to generate only 50 megawatt of power by average. Remaining 50 megawatt of power, no need to generate. So this it tells the average demand 50 megawatt by plant capacity of 100 megawatt, it gives only 50%. That means 50% of generating station is only utilized properly. The next factor is it's about the reserve capacity. It's not a factor, it's about the value, how much power is in reserve. Suppose for example, if there is a sudden increase in demand for a shorter period of time, then the generating station is capable to support for that increase in demand. It is the difference between the plant capacity to the maximum demand in that station. For example, take the same 100 megawatt of generating station and on a particular day it meets the maximum demand of 80 megawatt, then we can say remaining 20 megawatt is in reserve condition. Suppose in the same load area, if there is an emergency of 20 megawatt for a shorter time span, then we can utilize that 20 megawatt for that shorter span. Suppose not only for the same area, if suppose there is a requirement in another area, if it is there 20 megawatt of power is requirement in another area, then we have to generate the power that remaining 20 megawatt and we can supply to that next area also.